This is a problem from the Putnam exam in some year. Don't forget the year. But this is a A5 difficulty level, meaning very, very difficult. Most difficult one problems are A6 or B6. And so for this problem, there is a elementary solution without using parametric integration or Feynman integration. But here, first, we will look at how to use Feynman to solve it. Later, in a future video, I will show you how to use the elementary method, just using basic substitution. Now, here, using, we're going to let x have a parameter a in front of x as our parametric function. Let's call I of a equals integral from 0 to 1 plus x squared log of 1 plus ax. So meaning as the value of a changes, the whole definite integral also changes. For example, if a is equal to 2, then we integrate this definite integral. There is a constant coming out. So that's my output. If we input a equals 3, then that's another different value of constant coming out from this definite integral. So we have input, output, input, output. It's like a machine. So this is in fact a function in terms of a. Even though different values of a may result in the same result, but they may also result in different results in many other cases. But for a single value of a, only result in a single value of output. So this is a legitimate function. Okay, this is fine. So if you are wondering why don't we just use some other a appear in other places, like can we let x squared become a times x squared instead of a appear here? That's not a very good choice. Can we let 1 be a plus x? Still not very good choice. The reason we let x becomes a times x is because later it'll turn out to be nice for us to cancel out something. And also we don't want to deal with logarithm because it's also very head scratching to deal with. So that way we can get rid of the logarithm. But this is just a matter of experience. The more we deal with such integration, the more familiar we're with it, the more likely we're going to know which parameter to insert to. So IA is equal to, so we differentiate with respect to a. So I dash a is now equal to, we can actually, in fact, here we want to, first do the integration, then differentiate. But you know what? We can first differentiate inside, then we integrate the whole thing. We can actually switch the order of integration and differentiation. So the reason is because I'll maybe make a video in the future to explain the reason why. But this is easily verifiable. So 1 plus x squared, so x is a constant, a is a variable. So here we just say, keep the constant. And differentiate with respect to a. Then we just simply multiply, so 1 over this quantity, so 1 plus ax is at the bottom. Then there's a constant in front of a, right? That's x, just times x, dx. Okay, so this still contains a, and so this whole thing is still a function of a, right? So the derivative. So now we can deal with in this quantity using splitting the rational function. So So this quantity, let me just rewrite it as, I'm going to use ax plus b over 1 plus x squared plus d over 1 plus ax. Split it into those two rational equations. We're going to figure out the value of a, b, and d later. And that is equal to 1 plus x squared times 1 plus ax. X. All right, so we just combine those two. We have, let me just use 3 dots to represent the bottom. So this, we have this times that, this times this. So ax plus b times 1 plus ax plus d times 1 plus x squared. X. And we simply expand this one. We have, so let's look at the x squared terms, right? This times that. So here is a d times x squared. So a times a plus d x squared. X terms, right? So this times that times this. So capital A plus b times a. So plus capital A plus b times a. X term. Then the constant b plus d. So that means we actually, this equal to x. So meaning we don't have x squared term. That means our constant should be, this constant should be 0. So a times plus d should equal to 0. X term, right? This constant should be just 1. So a plus ba equal to 1. It's our constant, 1. B plus d is 0 because we don't have a constant term here. So b plus d equal to 0. Remember, we just here we treat a, b, c. How do a, b? We treat a as a constant, and we treat a, b, d as unknowns. So 3 unknowns, 3 equations. Fine. So from this equation, we know that d equals minus b. So d equals minus b. This is what we know. So substitute this d into first equation. We have a plus minus b equals 0. Substitute, we have using second equation, right? This equation and that equation. So let's say this is my equation 1, that is my equation 2. C times a. Okay, I'm gonna times second equation by a. So little a. So capital A times a squared minus b times little a equal to 0. This is my equation 3. And equation 1, equation 3, remember plus ba minus bo, we can just simply add them up, cancel out this term. Now, when we add them up, we have, so capital A plus capital A, little a squared plus 0 equal 1. From here, we can easily figure out capital A, right? Capital A is equal to 1 over 1 plus a squared. 1 over 1 plus a squared. Then we can easily figure out B and D. Right? So using substitute A into maybe here to this equation, capital A. Maybe just substitute it into equation 2, but anyway, either way is okay. So substitute here, we have little a times capital A, so little little a times capital A. Capital A is 1 over 1 plus a squared. Equation 2, what does it say? Minus b equal to 0. So b is easily a over 1 plus a squared. D, what's d? D equals minus b. Okay, d equals minus b. So minus a over 1 plus a squared. Now we have a, b, d all sorted out. Right? So we can say, okay, I dash a now is easily equal to integral 0 to 1. So I'm still gonna use the a, b, d because this is too much for me to write down. So ax plus b over 1 plus x squared plus d over 1 plus ax split it up dx. Okay, then we can easily say that, okay, here we simple because we no longer have any logarithm. Just differentiate, integrate with respect to x. This should be easy to, because this is only a rational function. Rational function should be easy, right? So here we just split this and that. So the antiderivative of capital Ax over 1 plus x squared should easily be logarithm of 1 plus x squared times some constant. So no longer need the integral sign. So it should be easily be logarithm of bracket 1 plus x squared. I'm going to figure out the constant. So here, first of all, we have a constant capital A. Right? If we differentiate this one, we have chain rule 1 over 1 plus x squared times 2x. Here we have ax. So to cancel that out, we have to multiply by half a. Half capital A, if I'm correct, right? 2x, 2 and 2 cancel out, capital A appear here, right? No problem. Here, capital B over this quantity. This should be easily arctangent. Arctangent. Don't forget the constant B. Write down B here, B times arctangent x. Evaluated from here. I forgot. Evaluate from 0 to 1. Evaluate from 0 to 1. Plus d over d is a constant. This is simply also a logarithm. So d times logarithm. Logarithm of 1 plus ax times some constant. What constant we times? Differentiate this one. We have a, so divide by a. This is my constant. Okay, so here we have this and that. So this should be easy to evaluate. Okay, we've established the our parametric function. It can be written like this, and we've also figured out the value of a, b, and d. So simply we can evaluate this one. So 1 becomes 1. So log 2. X is 0, then that's log 1. Log 1 is 0. So that is simply, so I dash A is times log 2. All right, so what is this? B times arctangent. Arctangent 1 is pi over 4. Arctangent 0 is 0. So plus pi over 4 times b. Okay, so what is this? This log. So log log 1 plus a, log 1 plus 0, log 1, 0. So log 1 plus a, what's d? D is this one, right? So d divided by a is, so minus 1 over 1 plus a squared. So this will actually become minus 1 over 1 plus a squared. Okay, so this one will actually become minus 1 over 1 plus a squared times log of 1 plus a. Okay, then we substitute a and b with a's. So I dash a is now equal to capital A over 2, that's half times 1 over 1 plus a squared times log 2 plus b a over 1 plus, so pi over 4 times a over 1 plus a squared. This is b. So minus 1 over log. Okay. Since we have this, and then we could find its antiderivative, right? Integrate indefinite integral. What is this? So here, indefinite integral of this should be, remember in the end we have a plus c, plus some constant. So here, half log 2 is a constant. 1 over 1 plus a squared is to be integrated. There's arc tangent a, right? So half log 2 arc times arc tangent a. Right? What is this? This again is simply pi over 4 times log of 1 plus a squared times some constant. So because constant should be, because in the end we have a different chain rule, so 2a, constant should be times half. So that's pi over 8. Pi over 8. Right? Pi over 8 log 1 plus a squared. 1 plus a, 2a. Yes. So minus this. We don't know this. This is hard to integrate. But if you realize that this is actually our desired integral, we just replaced x with a's, right? 1 plus a squared, 1 plus a, integrate. The only difference is that this is definite integral. That is indefinite. All right, so we just say, okay, minus indefinite integral of 1 plus a squared log 1 plus a dA. Right? As long as the variables are consistent, then that is essentially the indefinite version of our definite integral. And we can then use the fundamental theorem of calculus. And let's say, because we desperately want to know because we wish only if we could make it a definite integral by adding 0 and 1 here. We cannot directly do that, not straight away. We have to first, explain it legitimately. We have to say, okay, according to the fundamental theorem of calculus, if let's say we choose a way, so we reached one of the antiderivative of I dash a should be written like this, and we should plus a c, right? So we're determining the constant And remember, the since I of A is this one, so that means since if we, like I said, we've initially differentiated this one to get to previous expression. And so that means, right, we differentiate that to get to I dash A. So that means this is actually one of the many antiderivatives of I dash A. And this is also one of the many antiderivatives of I dash A. So that means the difference between this and that should also, they differ also by some constant, some C. Right, so that means the difference between I of A minus this also differs by some constant. So that means this can actually be written as this plus some constant. Log of 2 arc tangent A plus pi over 8 log of 1 plus a squared minus dA plus C. This C may be different from that C, but it doesn't matter as long as it's just a symbol, right? Just some constant, doesn't matter. Okay. So I'm going to determine the value of C. So how do we determine that? First of all, I say using fundamental theorem of calculus. So as long as let's say we have a changing variable upper bound integral. All right, as long as we have let's say the lower bounds is some constant, I'll choose 0 as my lower bound, right? Just so it's nice. And my upper bound is changing. It's a variable. What variable is it? I'll use A as my variable. In fact, I will use T as the 1 plus T squared log of 1 plus T dt. All right. So if remember, we integrate with respect to T from 0 to A. A is changing. A is the variable. Imagine if we differentiated, because we already know that the integrand is obviously continuous everywhere over this interval, right? There's no tricky point here. Log is fine. Log from 1 all the way up to, so A is of course greater than 0. So we won't have, so when the bottom is also safe because, right, we won't have some 0 at the bottom or won't have something that's unbounded. Everything is safe, looking fine. So this is actually continuous over this interval. Okay, then we can just say that according to the fundamental theorem of calculus, if we differentiate this one, right, this is it. I denote this one as capital F of A. All right. I consider this a function of little a. As A changes, the whole value of this integral also changes. Input, output, input, output. It's a function of little a, in fact. Now, if we differentiate with respect to little a, right, capital F dash A, what will happen? Well, according to the fundamental theorem calculus, this derivative is actually the integrand when we replace t with a. All right, that's according to the fundamental theorem calculus. Now we know that since the derivative of this function is equal to that, that means this is actually one of the many, many antiderivatives of this function. And this is also one of the many, many antiderivatives of this function. So that means the difference between this function and this function should only differ by c, some constant again. All right. So that means this indefinite integral, also consider it as a function of little a, can be written as capital F of a plus some constant. It could be different from that constant, but still we can just write plus some c, it's just a symbol. So in fact, we can rewrite this minus capital F of a, bracket plus some c. Get rid of bracket, still minus some c, but still plus some c, because it's just only symbol, right? Just some constant. This is fine. I'm going to determine the value of c just very soon. And keep in mind, capital F of a. Well, what's capital F of 0? Capital F of 0 is just 0 to 0, simply 0. Capital F of 1 is from 0 to 1, integrate, is equal to our desired integral. Keep this in mind. So here we could, even though I remember that's why I use this, this trick as a bridge to transition us from this indefinite integral into something that's more certain. Because here we cannot directly use 0 to 1 just straight away. This is not allowed, right? But here we can, so this is nice, this is better. Now, we continue work from here. Let's find out I of 0, right? To help us determine C. I of 0, what is that equal to? So arctangent 0 is 0, 0 times that 0. Log 1 plus 0, log 1. Log 1 is 0, so 0 plus 0, 0 equal to F0, like I said previously. F0 is 0 to 0, integrate 0. C, we have determined C, right, equals C. I of 0 equal to C. We have to find out what's I of 0. I of A is equal to that. I of 0. So log 1 plus 0. Log 1 is 0. 0 integrate is still 0. So I of 0 is in fact 0. So C is equal to 0. Right, so C is gone now. So this looks much better. So let's find out I of 1. Remember, so 1 becomes A, AX. If A becomes 1, then we have the original integral, right? So just need to find out I of 1. I of 1. So arctangent of 1 is pi over 4, right? So that's pi over 4, that's pi over 8 times log 2. So this becomes 1 log 2 plus pi over 8 log 2. What is this? Minus f of a plus 0. F of a. Sorry, f of 1, right? Because we let a become 1. 1, 1, 1. A becomes 1. Capital F of 1. Capital F of A, capital F of 1. So A becomes 1. 0 to 1 is our desired integral. In fact, let me just write it down. Capital F of 1 is indeed our desired integral. I, right, denoted as I, is equal to I. So minus I So minus I of 1. Of course, I of 1 is simply 0 to 1, 0 to 1 is simply I. In fact, I of 1 is A becomes 1. Integrate from 0 to 1. 0 to 1 is our original integral, I. Right? So this is also I. This is minus I. Right? Minus I moved over there. Plus I. Twice of I. Twice of I. That's I was also I. Twice of I equal to this plus that. Pi over 4 log 2. I is divided by pi over 8 times log 2.